So let's take a moment and see if we can analyze why we're getting the results that we're getting for the performance of selection sort as the size of the array grows. We can think about how much work it takes in order to sort an array using selection sort by focusing on the number of times we need to touch a particular array element, or how many times we need to visit it. Now, if you think about the algorithm, what it entails in that first pass is we have to look at every single element within our array in order to know for sure that we've found the smallest one in that first pass. Well, if our array contains n elements, then that first pass is going to take n visits. And then when we're done with those n visits, we're going to have to visit the first element and the smallest element again in order to swap them. So one pass through our selection sort algorithm takes n plus 2 visits. Well, we know we don't stop right there because we shrink our tail by 1 and then we do it again. Well, the second time, it's not going to be quite as long. It's going to take n minus 1 visits in order to find everything in the tail, and then it's going to take 2 more visits in order to swap it with the second lowest element in our array. Well, then we're going to have n minus 2 plus 2, n minus 3 plus 2, and we're going to continue going all the way up to the end when we look at the last 2 elements, search 2, and then swap 2, possibly, if it needs the swapping. So that gives us a way of thinking about how many visits are necessary in order to sort a list in a general sense. So let's look at the math for that. What we're going to do is we're going to put all of those visits together in one formula and try and add them up. We know that that first pass was n visits plus 2 to swap. The second pass was n minus 2 plus 2 to swap. N minus 2 plus 2 to swap. All the way down to 2 plus 2 to swap. That gives us the first formula in that selection there on the slide. Now what we're going to do is we're going to regroup the elements. We're going to regroup the elements into the 2's for swaps and the number of times to visit. So on the right-hand side of the formula, you see n minus 1 times 2. That's how many 2's to swap there were. We had to do a swap for every element except for the last one. So n minus 1 times 2 swaps. Then on the left side of the formula, we group all of the time that it takes us to do the passes through. So n plus n minus 1 plus n minus 2 all the way down to 2. Now it turns out that we can simplify the sum on the left-hand side of that formula. The equation for n plus n minus 1 plus n minus 2 plus n minus 3 all the way down to 1 is n times n plus 1 over 2. We subtract 1 from it because we're not going down to 1, we're going down to 2. And then the second half of the formula, plus n minus 1 times 2, remains the same for the swaps. Now we have a nice compact formula that represents the number of visits that were required in order to do a selection sort algorithm based on the size of the array that we're working with. And if we multiply through all the numbers, we end up getting 1/2 n squared plus 5/2 n minus 3. Now, when computer scientists look at an equation like that, what we're interested in, is understanding the performance as n gets very large. And as n gets very large, the term minus 3 is going to have very little impact on the number of overall visits that we see. And in fact, the term 5/2 n is going to have very little overall impact. And what's going to dominate the growth of this function is the 1/2 n squared term in this equation. Because we're interested in comparing the growth between one end and a second end, we're going to take the ratio of those two. So we're going to end up having 1/2 n2 squared over 1/2 n1 squared. And so the 1/2s are going to cancel out. And so because of that, when computer scientists talk about the efficiency of an algorithm, they use big O notation. And that big O notation means we're going to consider n as it gets very large, and we're only going to be concerned about a number that compares the ratio between two different numbers. So that's order n squared. And that analysis helps to explain why, as you look at the graph for running time of selection sort as n gets larger, it looks like it goes up as n squared. So the number of visits is on order n squared. That's how we use the term, on order. We use that big O notation to describe the growth rate of a function or an algorithm. So using big O notation, we say the number of visits is order n squared. What that means is that if we double the size of our array that we're sorting, the amount of processing time that it's going to take is going to go up by 4. That's troubling because it means that just because we got a bigger array doesn't mean we take a little bit more time. It means we take squared amount more time. So if we double it, it goes up by 4. But if we go up by 4, it goes up by 16. And if we go up by a factor of 10, the amount of time is going to go up by a factor of 100. So that the time it takes to sort these arrays is growing much faster than the size of the array. And that's a big red flag. Generally, the way that you convert something to big O notation is you find the fastest growing term within a function, you take away any multiplicative constants from the front of it, and you get rid of any smaller growing terms, and then that just becomes that order n squared, or whatever the fastest growing term is, becomes your efficiency for that function. Okay, thank you for your attention.